Welcome back to the Explainer. If you follow AI, you've probably heard the golden rule. Bigger is better, right? Smarter models usually mean massive, computationally hungry beasts. But what if we've been going about it all wrong? Today, we're unpacking a fascinating new paradigm in AI reasoning with a model called BDH-CQ. It's an architecture that challenges pretty much everything we assume about how AI needs to process information. Okay, let's dive into this. Here's our roadmap for today. Beyond chain of thought, inside BDH-CQ's architecture, smashing the cost frontier, testing visual generalization, and scaling latent reasoning effort. Let's get right into it. Imagine this for a second. What if an AI didn't actually have to waste time and your money thinking out loud, token by token, just to solve a complex problem? Right now, our most capable models lean heavily on generating intermediate language to work through logic. But think about it, we humans don't always verbalize every single step of a complex math or spatial problem, right? So why should an AI? Section 1. Beyond chain of thought. To really grasp why this idea of silent thinking is such a game changer, we have to look at the massive bottleneck dragging down current AI. Traditional chain of thought is autoregressive. It's literally thinking out loud. Every single intermediate step has to be serialized into a distinct vocabulary token, emitted, and then fed back into the model before the computation can even continue. That eats up massive amounts of tokens, latency, and raw computing power. Latent reasoning, though? That's like silent, internal thinking. Instead of verbalizing every single result, the model repeatedly transforms a continuous hidden state. It's exploring multiple solution paths in parallel inside this massive high-dimensional workspace without ever spitting out a natural language token until it is absolutely ready to give you the final answer. The big takeaway here? It entirely removes natural language as a mandatory requirement for internal computation. Section 2. Inside BDH-CQ's architecture. So how do you actually build a silent thinker? Well, let me introduce the star of today's show, BDH-CQ. It's a highly specialized reasoning system that combines in-context learning, the ability to learn a brand new skill from examples right on the spot, with recurrent latent reasoning. And it does all of this to solve queries without any serial narration. But honestly, the most staggering detail here is its size. This entire configuration runs on a mere 150 million parameters. In a landscape where we're measuring frontier models in hundreds of billions of parameters, this thing is incredibly compact. The researchers get into some pretty heavy math in the paper, but it elegantly boils down to a three-step architectural flow. Step 1. The model sequentially ingests the provided demonstrations into a recurrent memory state. And it doesn't just smash them into one static vector. The memory actually evolves as it encounters new evidence. Step 2. Once it gets the query, it kicks off iterative computation inside a hidden, latent workspace. Think of this like a closed-door mental scratchpad. This is that silent thinking phase we talked about. Step 3. Only after this internal reasoning is fully complete does the model decode and output the final exact answer. Zero intermediate language is generated. None. Section 3. Smashing the cost frontier. All right, so we have a model that thinks silently. Why does this actually matter to us? Just let this number sink in for a moment. $0.00007. That is literally less than 1/10 of a single cent. You could run 1,000 complex reasoning tasks for less than the cost of a candy bar. According to the paper's measured hardware time, this microscopic number is the actual computed inference cost per task for this model to perform complex visual reasoning. And when you plot exactly what that cost means for the broader AI landscape, benchmark scores against cost on a log scale, the results are wild. The authors report that BDH-CQ completely shatters the previously established cost accuracy Pareto frontier on the public ARC-AGI 1 evaluation set. It sits completely isolated from the curve of other models, establishing a brand new state-of-the-art when it comes to benchmark cost efficiency. Putting some hard numbers to that efficiency, the paper neutrally reports these state-of-the-art benchmarks. The 150 million parameter BDH-CQ hits a 29.5% pass at 2 score on the ARC-AGI 1 evaluation, again at that $0.0007 per task cost. Based on ARC price data from August 2026, the researchers calculate this is approximately 57 times cheaper than GPT-5.6 Luna running on its low setting. And even if you factor in the massive 80% API price reduction that OpenAI implemented, BDH-CQ still remains about 11 times cheaper. The sheer efficiency gains of latent reasoning here are just undeniable. Section 4. Testing visual generalization. To see how a silent thinker actually behaves in practice, the researchers put it up against the ARC dataset. These are sparse visual grid puzzles where every single answer is exactly verifiable. They tested some highly controlled generalization families here. They froze the model and systematically threw tasks at it like propagation, which is extending a color to a boundary, copying, where it duplicates a motif onto anchor points, ordering bars by height, and selecting cells inside nested frames. The goal was to see what happens when they really crank up the difficulty of a visual rule. The results revealed some truly fascinating nuances about the model's limitations, specifically highlighting the difference between extrapolation and execution. For propagation and copying, the model scaled absolutely flawlessly, scoring 48 out of 48 correct even as the distance and number of copies increased. But ordering tasks broke down sharply when it was asked to sort 8 items. The paper notes this is an execution limit. Basically, the model gets overwhelmed and outputs completely incorrect grid dimensions. Nested containment, on the other hand, fails at a depth of 5 frames. But the interesting thing here is the grid size is perfect. It just makes a localized relational error. The researchers proved this is largely a failure to extrapolate the depth of the rule from the examples, rather than a failure to execute the drawing itself. Now, what's really interesting is how the researchers probed the model's ability to compose multiple operations together. They didn't just want to know if it could do one thing, but if it could take 2 distinct concepts learned in context and combine them. So they set up tasks that required standalone relocation, standalone rotation, and standalone reflection. Then they tested demonstrations that forced the model to actually combine those spatial maneuvers together. And the behavioral results highlight a very surprising quirk. BDH-CQ easily handles spatial composition. It perfectly solved rotation mixed with relocation 72 out of 72 times. But when the researchers asked it to compose a color-swapping operation with relocation, it failed completely, 0 out of 72. It can acquire the color swap atomically in certain layouts, sure, but it entirely loses the ability to perform it when simultaneously asked to move the object. This shows us for sure that silent reasoning has some very distinct operation-dependent boundaries. Section 5. Scaling latent reasoning effort. We've seen where the model breaks, but what happens if we just let it think harder? Remember that latent continuous workspace we talked about back in step 2? Well, the researchers train the model across different levels of latent reasoning effort. At inference time, they can actually dial that effort up or down. And the raw data shows that increasing that internal effort directly boosts benchmark accuracy. At low effort, it scores 21%. Dial it up to medium, and it hits 27%. Crank it to high effort, and it reaches that peak 29.5% score. You pay slightly more in computing cost, but the model definitively gets smarter. This scaling curve proves that silent thinking scales beautifully. We've known for a while now that giving language models more tokens to write out their chain of thought makes them more accurate. But this data proves that purely internal, non-verbal latent reasoning scales in the exact same way. The more time the recurrent workspace is allowed to iterate on a problem in the background, the better the final answer becomes. We'll wrap up our explainer today with this really powerful quote from the authors. BDH-CQ makes memory, adaptation, and inference part of the same computational fabric. By dropping the mandatory requirement of natural language tokens, this 150 million parameter model achieves state-of-the-art cost efficiency, all while proving that AI can learn complex visual rules entirely in a silent, continuous state. Which really leaves us with a provocative final question. If models no longer actually need human language to reason effectively and scale their intelligence, what does the next generation of artificial thought really look like? Thanks for learning with us today.